Okay, thank you very much for the invitation. It's a great pleasure to give a talk on my recent work that is devoted to the study of the systems that could have order at any arbitrary temperature. So let me start with the topic that I want to cover. Firstly, I will briefly remind you what is spontaneous symmetry breaking, in general what we call it, and how we treat, or some known theorem about spontaneous symmetry breakings and when it occurs. After that, I will briefly remind you what is Largen model. No, I will study it both in just at zero temperature at ground state and at some finite temperature T, not in zero. After that, I will present you. Sorry, I will present you the model that we studied and show you that describes you a very nice conformal field theory. So just Or(n) plus some additional scalar psi, and I will show you how spontaneous symmetry breaking occurs here at any temperature beta. So specifically, I will show that maximum expectation length of psi is not equal to zero, even though this model has two symmetry under psi goes to minus psi. And if time permits and some time left, I will explain how thermalization occurs in this model. If time persists, if time allows. Okay, so let me start with introduction. All modern concepts of described model in condensed matter physics is based on the idea of symmetries. That we say that we study some particular model that has some intrinsic symmetries of the system. It could be some intrinsic symmetries like flavor symmetry, or maybe some chiral symmetry. Or it could be even like some usual symmetry, translation symmetry, so on. And after that, we study the structure, the behavior of the system at different temperature and different some external condition, and classify the phases of this method depending what kind of symmetries are respected in this model. For instance, if we consider just a bunch of some quantum mechanical particles interacting with each other, the system has translational symmetry that I can shift all xi plus a. And it seems that at first glance, the phase of this matter should respect the symmetry. But as we know, sometimes if we low temperature like long enough, we could have some phases that does not respect that symmetry. For instance, you have ice that breaks that symmetry. And there are some powerful theorems. For instance, there is famous Goldstone theorem stating that if you have a broken symmetry, then you have Goldstone modes, massless bosons. In the case of ice, just phonons. And from that, we can extract some properties of low energy properties of these models. So the concepts of the symmetries are very important. And there are some ideas about how symmetries should work. Ideas how symmetries should be broken. Based on the following heuristic argument. When we study system at some finite temperature T, we usually state that the partition function of this model could be computed the following way, as density of states here multiplied by e to the minus beta E. And usually we write that rho of E is just entropy factor S of E. And in the thermodynamic limit, we claim that this plate exponent, the factor that extends this exponent is extensive in volume in some sense. And we have the following factors here. Let's call it epsilon. Epsilon here. And when we study thermodynamic limits and volume to infinity, uh, we just need to study saddle point of that functional, of the function of some external parameters that you put there, or here energy. And that allows us to find what is actually the system is. Here is called free energy. And usual law states that if we study low temperatures, this factor is irrelevant. It goes to zero. Well, this factor is important. And this describes some ground state here. In quantum field theory, actually, we also know that we have spontaneous symmetry breaking. That at zero temperature, local unitary quantum field theory prefers to break one of the symmetries. For instance, if you have the following theory, force that has the following potential. The field theory prefers to live in one of these states instead of being spread among these two, like it happens in quantum mechanics. The reason is that since we study also thermodynamic limit, roughly speaking, the probability change from one vacuum to another vacuum, plus, minus, becomes zero. So roughly speaking, it means that if I put here minus and some local operators here, A1, A2, AN plus here, it would be some, let's not beta, let's call some coefficient C, CV. And the thermodynamic limit is vanishes to zero, meaning that overlap between these vacuum states is zero, and by applying only local operators, you will never be able to change this plus. Therefore, it forces us to state that we should consider only state with a broken symmetry. Symmetries. So we assume that our ground state spontaneously breaks symmetry, and some of the operators, say this order parameter operator phi, acquires a not, even though our system has a symmetry there that managed to relate this to each other. In quantum mechanics, this actually prefactor is finite, and that's why we get that our ground state is actually linear combination of them that respects the symmetries here. So from this consideration, we see that when we send temperature to zero in this model, though we have spontaneous symmetry breaking. Symmetry breaking. But as we increase temperature, it seems that actually this term becomes more and more important here. And entropy factor wins, and it wants to change our system. Let me be more specific here. So we know that as temperature goes to infinity, or beta that is equal to it goes to zero, we usually describe our system with the use of the density matrix e to the minus beta h. And what it tells us when if beta goes to zero, naively, we would have that rho goes to 1. here, and therefore if I compute some correlation function phi rho, here trace phi rho, I would get that naively the limit beta goes to 0. I would guess that is equal to trace of phi from identity operator. It means that my sectors that were different by plus and minus get equal contributions, and therefore we get that is equal to 0. So we get the following pictures that at small temperatures we have spontaneous symmetry breaking, that while volume parameter phi as a function of beta prefers to get some particular value v naught that actually could be selected by, there is a different way of formulating it by stating maybe that we have even large system, but we have some boundary condition here. That's what's it to say to plus. Plus, and after that, the sort of parameter inside becomes pick some particular value. But if I take beta to infinity, oh, sorry, beta to 0, this phi beta becomes equal 0. So this boundary condition actually is not relevant anymore for us. So it becomes equal to 0. So we have such a heuristic picture. But here the most important fact that this was based on the following observation, that we say that beta goes to 0, therefore this operator density matrix into the minus beta h goes to identity. Actually, since we are dealing with infinite Hilbert space, we should be very careful about what we define under this limit. There is difference. For instance, we can have big limit here, and this is the one that actually holds here, meaning that if I pick some state psi and phi here and compute the overlap h phi, then when if I take beta to 0, I will get that it's just equal to my overlap psi over phi to goes to 0. But there is also exists a strong limit. Stating that limit of the supremum of psi is equal to 1 of psi is the minus beta h psi goes to identity here. While weak limit is quite obvious observation in this model, the strong limit is the one that we should take care, because of only if strong limit satisfied, then we can make this assumption here that trace of phi rho vanishes when we send beta to 0. Sorry, there is 0. By the way, do you have any questions? If you have, please interrupt me at any point, and I will be happy to discuss here. Okay. Nevertheless, we have this it should be nice. It would be nice to prove first this property, and apparently there is a so-called Dobrushin theorem.
Sorry, can I ask you a first question?
What?
I didn't. One first question. Sorry, I didn't get why the trace of phi has to go to 0. So when beta goes to 0, the density matrix is 1, and you say that the trace is 0.
Trace of phi. We just know that for each phi there exists minus phi because of the two symmetry. That's why it's equal to 0.
Okay. See, thank you.
Is equal to 0. No, roughly speaking, you have a symmetry. Here you have u. Here unitary symmetry maps the trace minus phi, right? But u dagger phi u is just usually unitary operator, so I can just put it here, get identity, and it will get trace f. So I will get trace phi is equal to minus trace phi, so it must be equal to 0. Yes. Okay, so it's based also on the observation of the big limit, and big limit doesn't usually imply a strong limit here. But there is some called theorems in mathematical physics called Dobrushin theorem. Dobruschen theorem. And it was written for Ising model. Ising model here, and he proved not the variance that I told you here that a strong limit exists. He proved the following. So take and take it on the some. Sorry. Take it on some in some domain and put some boundary condition here, plus or minus here. After that, you can study the correlation function here. You can interpret them as some expectation value of some of your local operator with respect some measure mu here, mu plus or minus. And the Gaussian theorem stated the following: that if you take that there exists some beta star, such that for any beta less than beta star, these measures coincide here in the limit of in the infinite volume limit. So it just stated the following: that here we can send our domain to infinity. So we send the border to infinity, and the boundary conditions actually do not influence at all the dynamics inside of our theory. And from that we can conclude that the system must be in disordered phase, where phi, the average of phi, is equal to 0. So it's called Dobruschen theorem. If you think it's some hardcore theorem that only hardcore mathematicians can understand, it's just a simple idea. That, for instance, take Ising model again. That this was used here. We know that it could be written the following way, like that: sigma j and sum of all field configuration sigma i's. And after that, we can make a heuristic large beta expansion here. So I can replace it like that. Hyperbolic sine beta plus hyperbolic sinus beta sigma j. I can expand this for small beta. I can expel it in this parameter. If beta much less than 1, then hyperbolic sinus is also much less than 1. I can expand in this, and I can re-express my e to the minus beta as sum over the various passes here. It goes like that, like that, like that, like that. It's usual expansion, so it will be sine beta sigma 1 sigma 2, sine beta sigma 2 sigma 3. After that, I see that only closed path contributes to my partition function or correlation functions. Plus, it's obvious that such expansion exists, and from that we can conclude that order must be restored, that sigma equal to 0. But if you want to be much more refined, you should refer to as Dobruschen theorem, that roughly speaking, this expansion holds for some small beta star. That this expansion is actually valid and is not asymptotic, is valid, and has finite radius of convergence here. Here, and the other theorem, there states the following: that if you have some lattice system on, let's say, some Popov manifold across S1 and beta, and you send beta to 0, then you can prove that rho is equal to e to the minus beta h. Here is indeed goes to 1 in the strong sense. Strong sense when beta goes to 0. So roughly speaking, if you assume that I have some lattice domain compactified in one direction here, and after that I make this direction smaller, smaller, and smaller in sizes, my density matrix will approach closer and closer to 1 for such system here, strong limit. So there is some theorems, but as you know, as all theorems, there are some loopholes, and there is some experimental observations that sometimes we have some strange behavior of these limits, that sometimes we have first liquid phase, after that we have solid phase, after that we can again a liquid phase. I don't actually remember what kind of system it realized in real life, but you can find it somewhere. So this motivated us to find some field theories where such system could have this spontaneous symmetry breaking. Of course, you can refer this that we have the Dobrushin theorem, and like this theorem here it states that it's impossible for lattice system. But let me notice that when we go to the field theory, we usually have continuum limit. We send that we have some lattice system here. We have some UV regulator A here. Usually when we mean what we mean under the field theory is when we send A to 0 here. That every interaction that suppressed in this limit are neglected. And as you might see in these theorems, especially this one that I will be most interested in here, it was very important that beta goes to 0 here first. If I send A first to 0, then I will have continuum limit, and this theorem no longer will be applicable. So roughly speaking, here I interchange the limits here. And therefore, maybe we can find some models where such limits, where we have spontaneous symmetry breaking persistent at high temperatures. So is it clear what I have told so far? So this is some introduction. Okay, so such a nice candidate also it would be fine to find some unitary model. Unitary model. Plus it should exist at integer dimensions, say d is equal to 3. And plus it should be in some sense integrable. So we can extract some non-perturbative features of this model to study it. And one of the nicest candidates for such models is the large N model. Since I don't believe that it's it's not so well known, so let me briefly explain what this model is, and let me show how it works at finite temperature. So this model consists of the n scalar fields. You can put n fermion fields, and you will get so-called cross-Neveu model. But I will study phi squared and add the following term. Not phi squared squared. So we have usual free field theory with n scalar fields plus some interaction with respect to this ON symmetry. And note that I introduce the following factor 1 over n. Roughly speaking, if I set that phi I of the order 1, I will get that all of these terms now of the order n. Because of here, I would have that of the order n squared, but here it's suppressed like n. That makes it of the order n. Because of that, when I take first large n limit and goes to plus infinity, I will get that not all Feynman diagrams survive in this limit, only some specific one. Namely, the diagrams that looks like that. So-called cocktail diagrams. And because of there is like enumerative procedure how to compute all of them, it becomes very simple to take into account all of these diagrams and completely solve the theory in the large n limit. Let me show how it could be done. So I introduce my partition function as the integral over dfi e to the minus 1/2 u mu fi squared minus 1/2 m naught squared by I squared minus lambda naught 4n by I squared. I introduce additional field here sigma. It behaves like that. Like that, and its purpose of life of this sigma field is to disentangle this quartic interaction. squared. Actually, I can do even better a little bit and write it in the following way. Squared over 2 plus n over 4 lambda naught sigma squared here. Also, let me note that I will set a large n CFT here. It's just to not to worry about this UV regulator because of CFT are self-consistent and they exist at all energy levels there. That's why I don't need to worry at all about taking this limit or existence of some small lattice here. It just will exist at all energy scales. So it will be my complete theory. So I will try to find some parameters R naught and lambda naught. R naught is just m naught squared divided by lambda naught, where this theory becomes actually conformal. But now here I can integrate out the fields delta phi I. It gets it describes the following model. So phi I now enters quadratically in this action. So I can just take this Gaussian integral and take that my contribution from this field has the following simple form. Here's actually factor of n, naught sigma plus n for lambda naught sigma squared, like that. And now I notice that I have large parameter in front of my action. It's this n. And if I take n first to infinity, it means that I just study the saddle point approximation for this integral. And for that, I just need to find the stationary point for my field sigma. That brings me to the following simple equation. X is equal to R naught plus sigma divided by 4 lambda naught here. And I want to bring this system to criticality. For that, I notice that in this large n limit, sigma field plays here the role of mass for my phi I squared. So if I find from this some field configuration sigma star, it will be a potential for my fields phi I. And if the sigma star is just equal to 0, it means that phi I doesn't feel any potential and they become effectively massless. And therefore, I would expect that this theory becomes actually conformal. For that, I noticed that I need to solve this equation. This equation has some problems, namely that this is ill-defined. And to do that, I just subtract some infinities to make this equation consistent. And if I do it, I will get that I can just subtract k squared plus sigma, just 1 over k squared. After this subtraction, I will get some finite r that just equals to r naught plus k dk over k squared plus sigma of 1 lambda naught. And from that, I will see that if I send r to 0, then sigma is equal to 0 is a solution. And I can neglect by the term for sigma divided by 4 lambda naught. So I can naively say lambda naught is equal just to infinity here. Here. And after that, I will see that it describe me some CFT where I can find the dimension of my field of delta phi I 1/2. And after resigning some diagrams for the sigma field, I can find that sigma field has dimension 2. But let me take into account 1 over n corrections, because of that will be important for my next considerations. I will find that these two dimensions delta sigma is equal to 32 pi squared 1 over n. And for delta phi I, there is some formula, but I think it's not so relevant. Okay, it's not so important here. And now if I study it at finite temperature meter, I will get the same equation, but here I should replace integration over omega over my time direction by summation of the Matsubara frequencies. So my equation at finite beta becomes the following equation. Plus infinity dt minus 1 k over pi d minus 1 over n squared plus k squared plus sigma is equal to r naught here. That is equal for critical point just dt divided by 2 pi d 1 over k squared plus sigma, or just without sigma, just 1 over k squared. After that, we can solve this equation very simply. Find that sigma is equal to log squared square root of 5 plus 1 over 2 divided by beta squared. Here, find the energy and find all properties of this model. Here you see that it's kind of nice model, so we can study it at finite temperatures. Do you have some objections or questions about this model? Okay. You might have an objection that here you might say that this theory is actually cannot be thermal at any moment because we have very weak self-interaction lambda naught over n here. But actually, if one can check that at beta of the order 1, the energies of my states is order n, and it means that it involves n fields here, phi I1, phi I2, phi IN, say, and bit here that I can represent by the following strands. And the strands starts to interact with each other by these bubble diagrams. And at first glance, this bubble diagrams appears like 1 over n, but since there is n interactions of them with each other, it's mostly there is this n at minus 1 over 2 combinations, how I can put this sausage link between these two strands. I will see that actually, even though I started with a very small interacting system, a weakly interacting system that I think constant is 1 over n, this combinatorial factor becomes quite huge. That completely makes this interaction strong. I will have 1 over n, which is pi by n and minus 1 over 2. The interaction becomes n. So we see that actual interaction becomes big, that makes the system thermalize. So we see this nice model that actually finite temperature thermalizes. So maybe by somehow modifying this theory, we can construct some interesting model that has spontaneous symmetry breaking. And for that, I just will study the following model. So I'll take my ON model again. Let me write this introduction like that. Already critical here. I can persuade you that the interaction has the following form. Here, notice sigma field, roughly speaking, imposes the conditions that phi I squared vanishes here. It's very important. Now I will just add some additional field psi squared here, just free scalar fields that doesn't know about existence of my OL model here for a while, so just like two universes living at the same time. But now I can introduce the following potential. For a while, let's consider the following case, 3 between D and 4 for a while, and introduce the following interaction, T sigma psi squared. You may note that it is the only free parameter in this theory. Theory that allows interaction between these two models here. Also don't allow self-interaction for psi here. Because of, you can check that this has exactly dimension d, so it's marginal operator, therefore it can fall to some new theory. Here, you might ask me that I could have introduced, say, sigma squared psi to the squared, or phi I squared psi squared, but you can check that if I introduce psi squared, I can always shift sigma by psi squared and completely forget about the existence of this term. And sigma squared psi squared has dimension d plus 2. So it's more than t, so it's an irrelevant interaction, and I completely can neglect it in the IR limit. So it becomes irrelevant operator, and we don't need to worry about this, and need to worry only about this term here. And after that, in 3 between d and 4, I can write down beta function for this interaction beta t, and find that it has the following form. Alpha t over n plus b t cubed over n. This alpha tm comes from the renormalization of the sigma field. Sorry, let me be more careful. In the Largian limit, strictly Largian limit, you will find that this operator is marginal, exactly marginal. So I can set t to any value in the Largian limit. But if I want to be precise and take into account 1 over n corrections correctly, I need to check whether it flows to some non-zero point at t goes to infinity. So that's why I need to write down beta function at 1 over n order. It comes from this from these two diagrams. One of them is just corresponds to renormalization of
May I ask a question in the meantime?
Sure, yes.
So the fact that the beta function is 0 actually at leading order in n, this basically means that you have a conformal manifold at large n that collapses in some point at 1 over n, right?
Yes. So if you pick this t is incorrect, you will not have a consistent 1 over n expansion. Therefore, you cannot conclude that the theory exists at finite n.
Okay.
So you need to find the correct t at which 1 over n expansion exists, and that's what I'm doing.
Okay. Thank you.
Here, roughly speaking, beta function here starts not from order 1, starts from order 1 over n. Here. Is it clear what I...
Yes, perfect. Thank you.
Okay. So now I have the following diagrams that I should take into account. One of them is quite simple. It just takes into account renormalization of the this interaction by itself, by self-interaction, t. Here, the propagator of sigma field contains 1 over n factor. Here, plus we should take into account that dimension of the sigma field changes here. So there's some diagrams that I don't want to draw here. Okay, I will draw it. It's just sigma, like that. If you take this into account, these two diagrams into account, you will see that they have the following structure. Here is t plus beta t cubed over n. Luckily, we know that for t is equal to 1, this model must exist here. So we know that it has a solution here, and it must exist at t is equal to 0. So from that, using some theorem from basic algebra, we know that there exists a third solution there. So we know that it has solution t minus 1, and this will be t plus, if you put everything correctly, d minus 1, d minus 2 over 2 here. So let me discuss this solution here. Is it clear what I have done here? So just used some theorem, Viet theorem or something like that, just found the roots of this guy. More or less I argue that they must exist third real solutions. T is equal to 0 is very simple, just means we don't have non-interacting theory. It's okay, life could be simple. T is equal to 1 corresponds that we have enhancement from ON to n plus 1 mono. We already know about that. And we kind of could have predicted the existence of this point from the very beginning. But now we have also this solution, t minus 1, d minus 2 over 2. And it just tells you that this guy comes here with a minus sign. Here. So let's call it, let's just say it's equal to 1 because of precise numerical factor is not so interesting. And from that, we see that actually, because of this wrong interaction, if we have condensation of sigma, psi would have the wrong potential. It would have, instead of being like a vase, it will be upside down vase. It will be forcing psi to acquire some non-zero wave here. And therefore, we expect from this model that at fine temperature beta, psi must get some vacuum expectation value here. But since I promised you that the model will be some sort close to physical reality, I want to set this model not between 3 and 4, but directly at 3 dimensions. So let me now switch to d is equal 3 here, and try to place the same rule. After that, I will just analyze a large solution of these models here. For that, I will start again with this equation: phi squared plus 1 over 2 sigma phi I squared plus 1 over 2 sigma d mu psi squared plus 1 over 2 t sigma psi squared. But now life becomes much more harder in 3 dimensions because of now we can write the following marginal operator with 26. That could becomes quite hard. Before we had interaction psi to the 4, but it's relevant interaction, and we usually just tune it to 0. So it doesn't matter. Here, it's a marginal operator. It means that we cannot just easily forget it could be generated throughout our arXiv flow. That makes the study of this model very complicated. So now, along with this beta functions, we need to study. We need to also study the beta. Oh, sorry, just G. Beta function for this field G. Here, nonetheless, we can do this computation in 3 dimensions and find out that beta function does not change here, but here. But now we need to study beta function for our coupling G, and it's quite complicated because we need to take into account a lot of diagrams. Let it be a little bit naively here and just try to draw them here, which one contributes in the larger limit into G. And I will see that the following diagrams contribute naively. Let me state it like that. Like that. And like that. So this is usual change of my renormalization of field renormalization of psi. So I just change the dimension of the field psi. This is responsible for the change of the dimension of the field psi to the 6 here. And it's just usual interaction here. And we have this term. Here, note that this and these guys are proportional to G. And roughly speaking, these diagrams are taking into account how my term psi to the 6 changes its dimension in this theory. So it could be easily understood. Here, this is exactly what I was trying to warn you from the very beginning. This, even though I could have started with G is equal to 0, presence of the interaction like that, psi sigma, generates this diagram. You can check that inside we have d3p divided by p to the 6 coming from the psi propagator, multiplied by pi to the cube coming from the propagator of the sigma field. And you can see that it becomes divergent, giving us non-trivial beta function, and therefore generate our field. Sorry, not field, generating our interaction psi to the 6 here. But let me just write naively this equation, and I will see that it will be equal to 128 pi squared m gt squared. Also, I forgot to mention that I will scale it like n squared. You can check that it will give you consistent perturbation theory here. That these diagrams becomes g to the divided by n cube, and this will become c to the 6 divided by n cube. But nonetheless, I will get these terms. There is some big number, p squared m, t to the 6. And now we encounter the following problem here. Because of let me study t is equal to 1, it tells me that I should include some non-zero g. And we know that is completely incorrect, right? Because we know that from the study of the large n models that such term is not allowed. First of all, because of though we don't write it. Second of all, because of sigma phi I squared just sets phi I squared to 0. And second of all, that even if I just consider what this guy behaves like, I will see that it's strongly irrelevant. So you might ask me what's happening here. And the question is quite simple. We were really surprised about that. Apparently, in 3 dimensions, we should be very careful in this study and correctly analyze sigma field here. In large n limit, sigma has dimension 2, and usually we would write dimension 2, and you compute the OP coefficient, you will find that it's equal to 0, leading OP coefficient. But actually, it's not true. This is strictly the large n limit. This the dimension of the field has 2. We can write another 3-point function that is invariant under conformal transformations. Usually, just like it's this product of scale functions. Here we can write the following function. So we have such contact term. Here, just some coefficients will be computed using just very simple perturbation theory. This is conformal invariant, and this guy must be taken into account. Thanks to the presence of this guy, we have to write down another dozen diagrams here that completely makes theory already quite complicated. But after that, it completely modifies the theory and tells you that it is equal to 1. It becomes what we want. It just tells you that turn it off. After that, sorry, I got completely distracted. I will end soon. After that, we take into account, we'll see that t is equal to 1, beta function vanishes for g is equal to 0. For t is equal to -1, we will find that there exists some g that is positive. That is positive, and therefore it gives us a nice CFT with the nice properties. Okay, so let me study now large n limit of this model. So let me start from d wasn't 0. So action becomes 1 over 2, g phi squared plus 1 over 2, g psi squared, plus 1 over 2, sigma phi I squared minus psi squared, plus psi to the 6 divided by n squared by some g. Between 3 and 4, we can forget about that. Let us analyze it's only is equal to 3. Let us analyze the large n solutions of these equations. We will find that they have the following equations. Let me be plus sigma is equal to phi squared minus psi squared. Sigma phi is equal to 0, sigma psi is equal to 0. And now, if I assume that sigma is not equal to 0, I will find out that phi I and psi I must be equal to 0. That sets me to some particular point that what's found in the large limit. But actually, because of presence now of the minus psi squared, I can find another saddle point that has lower free energy, that sets phi to 0, still sigma to 0, but psi is not equal to 0 here. I can find the solution and find that it has low energy. And from that, I will conclude that psi squared is not equal to 0 here. And in the large limit, it just takes the sigma must take some particular value, V naught here. That is equal to gamma d minus 2 over 2, sigma d minus 2, divided by 4 pi d over 2, psi to the power of d minus 2, psi squared, sigma squared. So from that, you see that at large n, at finite temperature beta, between 3 and 4, such a model prefers to have psi at any temperature beta with some non-zero value of psi here. The same analysis could be done for the theory d is equal to 3, and we can find out that this particular model, the value of psi squared becomes 0.05963 divided by psi There is analysis similar to what I have wrote, but a little bit more complicated. And from that, we conclude that we have spontaneous symmetry breaking at any temperature beta. Of course, it's not surprising because of I studied CFT, right? And if just find spontaneous symmetry breaking at some temperature beta, it must exist at all temperatures beta, right? Because of biascale transformation, we can relate for CFTs different temperatures beta. So you just know that if we have operator O, scalar operator O, temperature beta, it depends on temperature completely fixed. And if it's on R2 cross S1 beta, and if we know that some operator that expects C2 symmetry prefers to have non-zero B naught, then we would have spontaneous symmetry breaking at any temperature beta. Here we just presented CFT. And the last but not least, let me just comment a little bit why why we would expect it here that such model would have this time symmetry breaking. So roughly speaking, where does Dobrushin theorem breaks down here? For that, let me know that if I regularize the theory on a lattice here, I could say that I have a bunch of vectors as Si at each side of my lattice Z to the D, right? And I would have some interaction beta Si, Sj, I, J, plus some constraints that's Si squares, squares to 1 here. I could have done and assume that here just some psi I squares here. Here I could have done the same thing that I have done for the Ising model. So when I integrate over possible DSIs here, Sj plus C plus I squared minus 1 at side I. Here I could have spent it in beta, but this expansion would have been nice because of, for instance, this I expand say S1. Let me say that I have correlator. I want to say correlator S1, S2. I expand in S1, S2 beta, and after that I integrate over my space, and this integral is finite. Therefore, I could have kind of argued that my large beta expansion exists for this model. But now you may notice that actually what I'm doing here, I'm replacing here sign from one of the sign of psi I from plus to minus here. So instead of studying SI living on a sphere, I studied living on some hyperboloid here, some on de Sitter or anti de Sitter space if you want to state. And when I will do this expansion here, I will encounter that this my integral does not converge here. That integral is one. So for the sphere, I can prove that Sj is equal just to delta ij multiplied by the volume of the sphere here. But if it was anti-de Sitter, this does not hold. And from that, I could have concluded immediately that my large beta expansion does not work, and therefore I wouldn't expect here to have solution theorem holds here. And from that, we kind of could have expected from the very beginning that this model cannot have restoration of symmetry at high temperatures. Okay, I think my time is going to the end. Okay, thank you very much for the invitation.
Thank you, Fedor.
If you have any questions, I will be happy to answer.
Okay, thank you very much.